So today I want to talk to you about the missing part of Nix and where to find it. A little bit about myself. I am a build systems engineer at Anthropic. I'm at lifecycle on GitHub. You may or may not have seen me before. And I used to do Rust builds at AWS, and before that I did build stuff at Google OpenAI. So I've been mostly just doing builds for a long time. And yeah, talk to me about build systems and sound systems, lens systems. So I want to start just talking a little bit about what this even is. Like what even is distributed build system? So what is a distributed build system? It's a system that efficiently runs builds across many machines, sharing the results between them and deciding which machine builds what. And this sounds pretty simple at first, but if you think about it, these properties are actually really hard to do correctly. Because if you're gonna run builds across machines, well, you already kind of need to make sure that those machines don't really matter. And if you're going to share the results, you need to know what is what. Like, how can you know for a fact that you can substitute something for something else? And you then just have to decide who to build it, which sounds to me like the easy part. They're not CI. So CI, it has to do with webhooks and GitHub and making sure when a new commit comes in, submitting jobs. The distributed build system is what actually is doing your build. So the CI is usually a customer for a distributed build system. So if you look at things like BuildKite, they have both. Usually CI systems have a distributed build system inside of them, but I'm focusing on that part that is inside of it. Because I think for a lot of us that do a lot of builds, it would be really nice if you could use that distributed part without having to deal with the CI part. If every time you want to do a distributed build, you have to push or commit, that's not a really great experience. So I'm going to start about talking about the pillars for this. So if builds run on many machines and the results are shared, what do you really need? You need hermiticity for sure, right? Builds is pure functions. The only way you can guarantee that you can have a heterogeneous fleet of compute and still have your builds make some sense. And once you get that, you get good caching, hopefully, so you don't have to rebuild things over and over and over again. Because again, if you have a lot of people using this very large distributed system, the more caching matters, right? The more important it will be that you don't rebuild spuriously. Provenance becomes really important because now you didn't build a lot of the things you're using. So what is that artifact even built from? What is in it? And signing. At this point, you have a large network of computers and a large network of people using them to build things. You would hope that you know which machine built which artifact, and with a cryptographic signature, you know who uploaded it to cache, and you know who submitted that build. If you don't have this, well, things get really hard. If you don't have caching, I hope you have a lot of compute to pay for it. Without hermiticity, great, you built works on my machine, but at scale. And without signing, how would you know which artifacts to invalidate if you do have a security issue in your build? And without provenance, well, how do you even know what you're building that for? How does Nix fare here? How does it come into play? So far, if you know Nix pretty well, you would be like, oh yeah, Nix is a distributed build system. So far, all the properties I mentioned, we have them. Hermiticity, we got sandbox, caching, substitutors, provenance. The DRV records everything you need for provenance, pretty much. And we have really high quality signing with multiple signers. So let's go back to our definition. Runs across many machines, I call this execution. And Nix does give us that. We have remote builders and remote stores. Shares results between them. We have caching with substitutors, great. Decides which machine builds what, coordination. Yeah, we have nothing for that. Nothing really. Nix gives you everything except the part that makes it distributed. What is coordination? So it's composed of a couple different parts. So first is scheduling. Who is going to build what? Who's actually going to be doing the building? Dispatching, which is actually just routing the requests to each builder. Lifecycle management, workers do go down. They run out of memory. They will have random health issues. You have to scale them up and down. and queuing, ordering, deduplication, retries, spurious builds. So I started searching for this. Like, does it exist? Is there something that I can use in Nix easily to do builds at scale, really fully distributed builds? And I found a couple of things. The first one was Yensid. This is a hat tip to Julian and Alex at Garnix. It's pretty cool. They just shoved haproxy in front of the SSH protocol, and then they let it distribute it among a bunch of machines. It's kind of janky, but like, if you wanted to code golf build distribution for Nix, I don't think you could do any better than this. It's pretty awesome how well it works for how little infra is behind it. The problem is you can't do anything that's really clever with this. So you can't do any really intelligent scheduling. You can't really understand, like hotproxy is not going to understand derivations. Hotproxy is not going to look at the derivation, figure out what dependencies it has, and then be like, oh, I should schedule on this host because it already has those in the store. So you're never going to be able to build something that's truly efficient with something like this, unless you, like, I don't know, go all in on modifying hotproxy, which you probably don't want to do. Then there's nixbuild.net. They're here. You should talk to them, Rickard and David. It's a pay-per-use SaaS build firm for Nix, and you can self-host it. They do offer licensing, and we use it at Anthropic. It's very, very good. And it's essentially what this talk is about. It's about, well, why don't we have this in the community? Like, it's such an obvious next piece for Nix. It's so clear that we've done all of these things to make this possible, but then we just didn't make it possible. And the obvious thing when you think about this is Hydra, but Hydra is not really an answer to this. First of all, it's more CI shaped than you'd like, and it just does way too much. Like Hydra does email. I don't want my distributed build system doing that. And Hydra used to be really bad, but thanks to a lot of work from the people at Helsinki, we now have the new queue runner, which I don't know if it's been released yet or not, but I think it's getting close. And the new queue runner is way more efficient, and it is getting better, but it used to be not very good. I thought to myself when I was looking at this, like, how hard could it be? You know, all the pieces are there. How hard could it be to build a distribution system for Nix? So I called a project Rio, and this is mostly the story about me failing to build it. So we had this long weekend in October, and I made a bet with my coworkers that I could do it in the long week in 3 days. Yeah, foreshadowing. My pride, which I lost. So obviously working at Anthropic, I have access to, Claude, a lot of Claudes. And I figured, with enough Claudes, I surely can do it. Enough Claudes and coffee, it will work just fine. So, by the way, these links won't work yet because I forgot to click publish, but after the talk it will. So for the V1, I thought, okay, I'm gonna build something that's a central broker that receives these build inputs and distributes them. I am going to try to get the SSH protocol support via this crate that I found from Tweet called Nix-native. The builders just register with the broker. Simple round robin scheduling. Should be easy enough. Yeah, first of all, the central broker is a huge single point of failure. So anytime someone sends like a curse derivation or anything and the broker processes it and crashes, your entire system goes down. So that wasn't a great idea. The Nix-native crate has a lot of unimplemented things and a lot of parts of it that don't quite work that well. And implementing the protocol yourself is not easy. It's way harder than you think. And a lot of the docs is just C++ code that you have to go and read. So I gave up on this pretty quickly and never even got it to work after iterating a little bit. I think halfway through, at the end, I think it was like end of Saturday, I was like, oh yeah, I'm done with this. So then I started early, like Sunday, like 2 a.m. on V2, which I thought, okay, let's go brokerless. I will use Raft consensus, no central broker. They will elect a leader, and then the leader receives the build requests, and then it will decide which of the other ones gets to do the build. I'm not going to implement the Nix protocol. That's way too hard. I'm just going to make a custom CLI that does the eval locally and then sends it over gRPC. That sounds like a good idea. And yeah, this seemed way better. Also, the builds would flow directly from the client to the elected agent. When you submit a build, you get back the address for the agent that was assigned, and then you tell it, hey, I'm me, here's the derivation. And this seemed nice to me because you don't have to funnel through all the derivations through the broker. Yeah, this didn't work. The raft part was really hard to build, even though it seemed like there were good crates and Rust to do this. It was really hard. Like I have never tried to debug something that was so cursed. The custom CLI, after using it for a while, I was like, I miss my normal tooling, and I don't want to deal with this. And I don't think anyone else would either. So why am I building it? Yeah, Heisenbugs, a lot of Heisenbugs. I spent hours and hours and hours just trying to understand why sometimes it would elect a leader, sometimes it wouldn't, sometimes it would assign bills to the wrong person. Like it was really, really messy. And then I gave up. Then at this point we already had Nix-build.net deployed or starting to deploy internally, and it was working great. And I was like, okay, I'm sick of this problem. It's not a good one. Up until winter break, when I got bored again, and I was like, oh, maybe now I've learned enough lessons. So let's use SSH-ng, none of the legacy SSH protocol, only the new one. Leader elected by the scheduler with a PG advisory lock. The workers all use a Fuse backend for the Nix store, which is really nice with the overlay FS for the build. And no normal Nix store for in S3 or anything like that. So there's a component that's called Rio Store that does chunked cache storage with FastCDC. Which is a cool paper, by the way. If people are interested in that, you should go look at the FastCDC paper. It's really, really fascinating. Yeah, implemented the protocol is hard, but actually Claude was really good at it once I just told it write tests that just run the Nix daemon and compare bit by bit that you get the same output. Once I figured out how to do that, it just churned through the whole protocol. So that was easy. Making consensus being roughly someone else's job, I think was a wise decision that saved me a lot of trouble. The Fuse part, I'm still fixing. So I don't know if that was a good decision or not, but when it works, it is really, really nice to just have full lazy fetching for the store layer. And the deduplication, full deduplication across all NARs is very powerful. Yeah, you can save an unbelievable amount of storage by doing this, which it sounds like cost at first, but if you have really fancy deduplication, that means you can maybe afford to shove your cache into like a ginormous EBS volume that just mounts to all of the hosts, which is way faster than S3. So I kind of, sort of found the missing part. So I think if you really just want to find it easily, just buy Nix-build.net. That's how you can find it. But if not, well, we have a couple gaps to fill. The protocol spec that we have to specify this stuff. We have to write a doc that people can read and understand and make it easy to implement the Nix protocol. Not just for this, but in general, I think we need to make the protocol like a first-class, well-supported video. Having libraries for this would be nice. This Nix stuff works, but it's all GPL free, and I didn't want to use it. And then the rest is all this real C++ code, and I didn't want to use it because I was writing all this in Rust. And everyone has been talking for a while, like if you've been following along with Snix and Fix, about how to change the store model to be more efficient, how to allow for lazy fetching, how to use the Fuse for this. Everything, there's pretty broad agreement that that's the way to go to make this better. We should just do it once, build this component once, and then we can all use it because it's kind of a reusable thing. So I think for me, like my big takeaway is, like we got the really hard parts right. The really difficult properties to guarantee, we got them. Like we have them and they work really, really well. The only thing that we're missing now is coordination. We're missing this central component that you can deploy easily and just send builds to and not worry about who's actually doing the building. And I know this sounds like an annoying, like maybe corporate problem, like, oh, you don't need this at home. I don't know. I would use this at home. I would 1,000% put all my 12 computers on my distributed Nix build system and then just do Nix build and not care where the builds go. And if you do this smartly enough, right, this would know that you have it running on a machine with 2 cores and one with 8 and one with 16, and it knows how to right size your builds because the P name, although it's kind of janky, is a pretty good indicator of what build it was. You can basically tag your builds with it, and you can do very clever scheduling and things like that. So I am building this. Well, Claude is building it. I'm telling Claude how to build, but he's doing all the work, not me. I have it mostly working. Right now, I'm still struggling with the Kubernetes parts of this. Right before this, I was trying to get a demo for this, and I thought I had it. I was like, oh yeah, this is definitely going to work. And then I ran into some really cursed, bizarro C groups staying inside the Docker container, inside another Docker container that I'm still trying to figure out. But today, if you don't want to run it in Kubernetes, if you just want to deploy it yourself, it already works. It just doesn't autoscale. But you can take the Rio build code and you can run the Rio worker on some of your laptops. There are Nix OS modules. Yeah, it works. And I will now, to celebrate this talk, open source it. What? Wait. Come on. Come on, baby. It's a lot of... Ta-da! Oh yeah, and also very importantly, I will... push all of the latest work. So V3 is now up. Enjoy, go look at it. All right, questions?
You can definitely there. You can like it is your remote do that, and you can set up big enough that was the thing. And you seem to do that with money dirty on the
Yeah, on the client.
and go. With that, it seems spirit single feel like it to say all up big. Good make it. Not sure I know you're a here. Run it is a hash and say for this thing and it at the that guy put in that to my net that and those note themselves she also consistent catch thing. I so only while and later roll and before.
The problem with that is how do you right size the allocation? Like if you had a fully homogeneous fleet, that would be perfect because it doesn't matter who gets what. But in reality, most of the time you want heterogeneity, even especially if you're deploying to the cloud where you can just now have capacity with the same SKU that you were using before, and then what are you going to do? You can't scale up. So
Pick up and get him pockets. You percent may get one. I could go get a different group.
but what happens if I have a build that only works on a machine that has at least 32 gigs of RAM and it gets bucketed to a machine that doesn't? If your hashing scheme puts Chrome on your Raspberry Pi to build. Yep. And there's also questions about like how much you can optimize it later. For example, you may have builds in a real environment that you don't care about how long they take. You just want to do them cheaply. Or you might have builds where you're like, no, I'm doing development right now, and I want really low latency. So instead of you, for example, measuring the average CPU utilization to save in history, you can measure the peak CPU utilization. So you can size them to as many cores as the build can take. So it gives you a lot more freedom with how you do the scheduling. Yeah. Anyone else?
Know what the accuracies of filter it can have. Can you call it if you
Yeah, so I actually thought Claude was very clever with how it did this. It built this Bloom filter setup where it keeps track of all the store paths that all the workers have, which it knows because it knows all the builds it submitted to each worker and it knows what each build depends on, so it can deduce. So then very quickly, when it's trying to schedule a new build, it runs this Bloom filter to find out which builder is more likely to have the most paths present. And then if it has the right size, it gets routed to it. I thought that was really, I wouldn't have thought of that, honestly. And I thought it was interesting. There's a lot more you can do for for scheduling things correctly. So one of the things that I've been trying to get it to implement is this paper that people in the Nix community have been talking about forever called tags, where essentially you divide your hardware into these groups. So you say like, oh, I have small machines, medium machines, large, extra large, whatever. And then every time you see you find a stable key for your build. So I think for Nix, P name's pretty good. Every time you see a new P name, you always allocate it to the smallest group with a deadline. So like 5 minutes. If it finishes, great. You remember that that builds on a small machine. If it doesn't, you move it onto the medium machine. And you go on until you find the right size, and then you record that. And over time, every once in a while, you try to move it back to the smaller one to see if it moves. So this is nice because it can combine both right sizing from a resource utilization perspective and from a like outcome, where you can just change the deadlines for each group to get really, really good latency and still have all of them right sized. Thank you, Tom. All right. Going once, going twice. That's it. All right. Thank you so much, everyone.